Hello and welcome to Completely Electrical STEM Show. We're going to have a look at some basic cable designs. I'm going to start with the three-phase motor with a bit of power factor, and I'm going to go through sizing the live cables and the C.P.C cables. And I'm also going to do both methods. So there's two methods to size your live cables and there's two methods for the C.P.Cs. I'm going to start with both the live cable methods and then move on to both the methods of sizing the C.P.C. And hopefully you'll see the difference. It's mainly about rearranging some of the formulas really to maybe get there a bit quicker rather than going back and forth and checking for compliance all the time. So join me down there. Righto, so where do we start? Well, let's just remind ourselves what we're calculating here. So our load is a three-phase motor, 6 kilowatt, and it's got a power factor of 0.8, so not quite perfect, producing a bit of reactance as you'd expect. It's an induction motor. I didn't state that, but it is. Induction. Our circuit length is going to be 30 meters, and we can use some existing conduit that has contained within it, didn't mean to write that, let's say two other circuits. Our supply is 400 volts, 50 hertz, three phase, and we got a ZE of 0.12 ohms. Now, design can go as deep as you want it to go, really, and you know, I just want you to remember this is for level 3. So there are lots of more detailed explanations out there, and if you're really going to get serious about design, then I can't recommend the IET's design guidebook. Actually, it's not that clear, you know, so it's not that easy to learn from, but it certainly gives you kind of pointers as to what you might want to explore a little bit more. But anyway, so this is just level 3, and with level 3 and any level actually, we always start with our design current. Now this is a three-phase load with power factor. So the equation we're looking for is going to be U times √3 times any power factor and times efficiency, but we're not going to bother with that. That's supposed to be a U, by the way, sorry. And you know, turning that into what we've got 6,000 watts divided by our U of 400, that's line voltage, times √3 times our power factor of 0.8. That √3 is, you know, like a standalone thing. Be careful that that doesn't extend over the power factor when you're putting it into a calculator. Which reminds me, where is my calculator? Oh dear. Why am I so unprepared? That's so annoying. One sec. Right, there we go. Calculator found. So where were we? So 6,400 times a √3, and then just press that little button there so it stops that hat going across. Okay, so we got 10.83 amps. Now that's per line or per phase, if you like. Yeah, 83 amps per phase, or per line. Get told off calling it the wrong thing, but you know what I mean. there's 3 phases, and each one's going to need to be able to cope with that. But it's not the end of the story, because we've got factors to consider. Now there's loads of these grouping factors, and there's one for pretty much any situation. And what it's doing is saving so much physics, like you cannot believe. And so they're always going to be, you know, slight approximate. And that's what I'm saying. You can go as deep as you like with design. You could calculate the exact amount of heat dissipated from the cable in the exact conditions, but you know, the amount of measurements you'd have to take from that site, you'd have to contact the cable manufacturer and know the thermal resistivity of their insulation and the tolerances. It just gets mad. So we use grouping factors, and we use, you know, ambient temperature factors and buried cable factors, and these factors have been calculated for us, so why not use them? Now, so let's just get these factors together. So in our situation, you know, we're not mentioning any kind of increase or decrease of ambient temperature, so we're just going to, you know, go with it as, say it's 20 degrees ambient. But we have got a grouping factor, because our circuit's going to be with 2 other circuits, and we're going to assume that they're loaded. If they weren't heavily loaded, and I think the figure's about 30% loaded, then it's not going to have too much effect. You know, the heat from these isn't going to migrate onto ours too much, and any kind of reactants or eddy currents or anything like that, we're not going to see too much of it. But we're going to assume that these are, you know, fairly well loaded, as ours will be. So we have a grouping factor. Now we need to look that up. So I'm going to go to table 4C1, that's on page 396. Now what we got, we're in a conduit, so we're going to be looking at this, the cable arrangement, bunched in air, on a surface, embedded or enclosed. So we're going with that one. How many circuits? Well, it's 3 in total. So we've got 2 other circuits plus ours. So our factor is 0.7. That was pretty easy. But you can see all the different types of factors we got for all sorts of different situations. Goes on, and honestly, I have looked into some of the maths behind it, and it, you know, it's not unmanageable. You can get through it, but day to day, you know, you'd spend all your life doing maths. And if you're running a business, this is the way to go, isn't it? So we got a CG then of 0.7. Now we're going to need that in a minute, but first we need to decide what breaker we're going to use. You can go really close to this design current, so if there was, you know, an 11 amp breaker, I'd choose that. But the next one up, you know, we'll just stick to MCBs for this. And being a motor, that's still quite likely. So which type though? Because it's a motor, it's probably sensible to use a type C. So our MCB will be a 16 amp type C, and that just allows a little bit of surge when the motor switches on. Okay, so this is our IN. It's the rating of our device. But now we need to apply these grouping factors with this, and that's where the IZ equation comes in. Now IZ is the amount of current our cable needs to be able to carry with all of the kind of installation methods in mind. And so to get that, our equation would be IN divided by any factors that apply. So there could be an ambient factor, you could have a grouping factor, you could be going through some insulation, there's factors for that. You could be using a rewirable fuse for some mental reason, and that needs a factor as well, and that's just because they're useless, so won't be needing that. But you might come across them in the real world and you might want to check this stuff, and so that's why it's important to understand what that is. It's 0.725, but you can find that in the regs around the same area. So let's apply what we got, and then we can choose a live cable from that. So in our case it's 16 over our only factor, which is 0.7, and that will give us, it's going to have the effect of, you know, going up from 16 plus, isn't it? Anything anything divided by a number under 1 is going to increase this number. So 16 divided by 0.7, and we get 22.86 amps. And so that factor, that heat, we could have, if we didn't have any factors, then we could have looked for a cable that can carry 16 amps. Be a bit close, but you know, it should be alright as long as there's no chance of overload. But because of this extra heat from this grouping factor, we're now looking for a cable a little bit bigger. You know, it needs to cope with more current through it, and that's to take into consideration, you know, the need to dissipate the heat. So that's what we're looking for then. And now we need to go to the current carrying capacity tables in the regs. Now we're not far away from them. The first one, now we're in a conduit, so we need singles. And it's on page 401. And it's table 4D1A, single core 70-degree thermoplastic insulated cables, non-armoured, with or without a sheath, in brackets, copper conductors. So singles. There are higher degree ones, but you know, we'll stick to 70 for now. Now you've got to choose the right reference method. In our case, we're enclosed in a conduit, on a wall or in trunking, etc. So we're going for B. We are 3-phase. So now we're looking for that current carrying capacity. So 22.86 is what we're after. And come down. Oh, that's close, 2.5, but not quite. There we go. 4 mil has an IT of 28 amps. So IT is the tabulated current to, you know, under certain circumstances. So our IT then, we got 4 mil. So we're going with 4 mil, which has an IT of 28 amps, and that's table 4D1A, column 5. It's kind of handy to just write that down, and if you have a look, these columns are all numbered, so it just makes it easier to, you know, go back on what you did if you've made any errors. So we've got a live cable. So this is our line conductors and our neutral conductors. They're all going to be 4 mil. But that's not the end of it. We need to check that for volt drop. So we need our volt drop equation. Millivolt per amp per meter times by the design current times by the length divided by 1,000. So we know that, we got that earlier. We know that, that's up there. We know the number 1,000, it's just 1,000. And then we're going to calculate a volt drop. Now the maximum volt drop we're allowed on this particular circuit is power. So that means we're allowed 5% dropped. 5% of the supply voltage, which is 400, so that equates to 20 volts for us. Now it's important to know we're dealing with a final circuit that is direct to the source, but if we had this circuit connected to a submain, then we'd have to take into consideration the volts already lost by the submain. So if the submain had lost 2 or 3 volts already, well then we've only got 18 or 17 volts left. Okay, that's important. It's not every time you design a circuit. So let's find out this millivolt per amp per meter number then, which is, it's essentially resistance and reactance, volts divided by amps is ohms. But again, they've made things very easy for us. You could get an approximation with that if you did milliohm per meter, got it up to temperature, times it by 2, you'd get a live and a neutral value. But as I say, look what they've done. So the table we were just on was 4D1A. If you just turn over the page, it goes from current carrying capacity into volt drop. Now, it's arranged slightly differently, so be careful. We're over here now because we're 3 phase. Reference method B, and we were 4 mil. So just bring your fingers together, and we get a value of 9.5. So we put that in our little equation, and we can put everything else in, times our design current, which is the amount of current that's actually going to be going through the cables. It looks like we're getting more current, but this is to take into consideration the heat. So we're making it bigger to dissipate the heat. It's not actually going to be carrying that, it's going to be carrying this. So 10.83 times the length of 30 meters divided by 1,000. Plug that in. 9.5 times 10.83 times 30 divided by 1,000. So we're going to lose about 3.1 volts, which is fine. Tickety-boo. Right, new page. So that's the live cables done. Just remind ourselves then, 6 kilowatt 3-phase motor and induction motor, power factor of 0.8. Our supply is the same, so 400 volt 3-phase, 50 hertz, and our ZE was 0.12, I think. So IB, same thing. It's going to be essentially P over V equals I. But just remember that you can't just put in any voltage here. The manufacturers has got that power by applying a certain voltage. I see people get confused with this all the time, like especially showers and stuff. They go, yeah, but if the voltage goes up, then the current comes down. It's just not true. A shower is a resistive load. The resistance hasn't changed. You increase the voltage, the current's going to increase. It means the shower will get hotter and potentially catch fire if it went high enough, But you can't just make equations up. You always need, every equation, you can only solve one unknown. So if you put in the power in, you need the voltage as well that goes with that power to get an accurate current. So anyway, mini rant over. For us, we're looking at this, and the power is 6,000 watts. Now it's obviously going to be the same as it was before. Of course it is. 10.83 amps. So, we're back to IN. That'll be 16 amp type C again. And we're going for a BSCN 60898. Okay, so far exactly the same then. but this is where it kind of flips. We're going to check out that volt drop equation first. Meter, and what we're going to do, we're just going to flip it on its head to go for transpose for this, and what that does gives us a maximum millivolt per amp per meter value, and then we go straight to that table and choose a cable based on that. Sometimes you get it right, sometimes it doesn't work. We still need to check it for current carrying capacity, which obviously we'll do next. So it's just the other way around really, but we're still checking for the same stuff. Now we know the maximum volt drop allowed. We said it was 20 volts, so we can replace that with just 20. And then we just need to transpose for that. So millivolt max times IB times, I'm just going to put L. So transposition, you'd multiply that out, copy it that side, cancel, and then you got 20 times 1000 is equal to millivolt per amp per meter max times IB times L. Then you would divide out this lot, copy it that side, and then you can cancel, and we end up with millivolt per amp per meter max equals 20 times 1000 divided by IB times the length. Okay, so we got that, and we got that. It was 30 meters, wasn't it? So I should write it. Millivolt per amp per meter equal to 20,000, 20 times 1000 divided by 10.83 times day. So our maximum millivolt per amp per meter value then, 61.56 millivolt per amp per meter. Okay, so we go to the volt drop tables then. We're still in the conduit, we're still using singles. So same cable. Oh, I went straight there. Look at that. So we are three phase, reference method B, and our target then is 61.56, and that's the maximum it can be. Well, it's all of them. Look, even 1 mil, it's only 38. So they're all under that number. So go with 1 mil. But we've already done this in the last one and it came out as 4 mil. So we know that's not going to work. But I'll show you why, or how we kind of prove that. So we said we're going to go for 1 mil. Let's just write that down. So 1 mil would comply with volt drop. Check. So we need to check. So this is how we do it. So we're kind of working a little bit backwards, and what we want is that to be equal to or greater than our IN, which is 16 amp in this case. So we need the IT value for the 1 mil in those circumstances. So go back to current carrying capacity tables. Reference method B, 3 phase, 1 mil, it says 12 amps. So we already know it's not going to work because it's less than 16 already. But you know, we'll go with it. And our grouping factor was 0.7, so it's doubly. I was going to swear then. None of these apply, so we don't have to go any further. But let's just go through the motions. And yeah, it's down to 8.4, which is half what we need. you know, by a long way. So that doesn't work. So what we do then, we go up to a cable that has this kind of level. So let's have a look. 2.5, that's 21. So we could try that times 0.7. So 21 times 0.7, 14.7. So still not matching that 16. So guess what? We're going to go up to 4 mil. 28. IT is 28 times 0.7. What do we get? Okay, so that's 19.6. So that works. We knew that anyway from method 1. But so we got to the same place anyway. Which method you use, kind of just up to your preference really, and what you're trying to do. I suppose it's just getting you to understand how it all works really. So our IZ then with 4 mil, you know, comes to 19.6. That's more than that. Happy days. If there was any chance that the circuit could get overloaded, then what you'd want is your IZ to equal 1.45 times your IN. And that just allows a bit of overload time, because MCBs, they're not going to, on a slow overload, it takes a bit of time for them to heat up and trip. And in that time, you might get a problem with the circuit. So it's normally going to be things like socket circuits, where you don't really have a lot of control or knowledge about what they're going to plug in. So places like care homes in the winter, you know, they're going to pull out all them heaters, they're going to plug them in. Same with like meeting conference centres, places like that. We don't know what they're going to turn up with. So, you know, you need to consider this. Also consider, you know, lighting circuits. People are going to add to them. So again, might want to allow for it there, but you know, that's down to the engineer's judgment. Now, so we got our 4 mil. It complies with volt drop, as we know, and it's just a different way of getting there, but you can see there's still a bit of back and forth here. So for me, this method works great for long runs. Long runs, small loads, works really well. You get there pretty much straight away. But yeah, that's method 2 for the live cables. Okay, so we've got our live cables then, 4 mil. Now we need to think about the C.P.C. So it's just, this is method 1. With method 1, you know, we're basically going to choose the C.P.C. and then check for compliance in a couple of ways. Our max ZS, we're going to make sure that we're under that, and we're going to check it for thermal constraints, so what's happening during a fault. So to, you know if we're under our max ZS, we need to calculate what our max ZS is. Now it's going to be different for every protective device, and the formula you need is that. Now UO is line voltage to earth, because we're considering a live to earth fault. Cmin is a voltage kind of factor, if you like. It just drops the voltage a little bit, and it just means that, you know, if you've got less volts, you're going to get less fault current. So we want to know that in the worst case scenario, we're going to get enough fault current generated to trip our device. And we use impedance to kind of confirm that. In numbers, that's going to be 230 times 0.95 divided by IA. Now IA is the current required to disconnect our breaker instantaneous, so using the solenoid bit. For a 16 amp type C, that has a so type C is a multiplier of 10, B is 5, D is 20. They do perform a little bit better than that, so You can always ask the manufacturers and they might give you a little bit more optimistic answers. But if we want to make ZS, that's one way. This is how we do it. So 0.95, 16 times 10. We get a max ZS of 1.37 ohms. Now that's, at full temp, it's running, so it's be at the limiting temperature, 70 degrees. So in a minute, we're going to need to calculate our R1, R2, but we need to get our R1, R2 up to that temperature, so we've got a fair comparison. So the equation to calculate a ZS is this. Now it doesn't make sense. This should be Zs, because you can't add resistance and impedance to get impedance. It doesn't really make sense, but so we are meaning Z, and the reason why we're just putting resistance there is because there's hardly any reactance in cables smaller than 35 mil, so we don't really bother. And like I always say, you can just go deeper and deeper and deeper, and if you look in the IET design guide, it does say Zs, but for these kind of size cables, there's no reactance really to put in. I mean, you could calculate it, and calculate inductive reactance, it's 2 pi FL, but it's the L that's the problem in calculating. And especially with singles, it's not uniform, is it? It's not bunched in exactly the same way all the way through. In a cable, like a 3-core or something, or a 5-core, they're together and predictable, so it's easier to kind of calculate that. So for submains and big stuff, it might be worth doing, but for these kind of things, we're just going to use the resistance tables, either in guidance note 3, page 148, or on-site guide, I think it's page 196 or 198, it's table I1 anyway. We've already got this, it's 0.12, so we can put that in already. And we need to calculate that. So the equation for that is milliohm per meter times length times a temperature factor. Like I say, we need to get it up to that. I'm just going to call it TF, whatever. Temperature factor, and that's been done for us, but just know that these correction factors, they've been done for us, but it's just down to the fact that copper, it increases its resistance by 0.00393 ohms per degree C. I've done a video about all this, so check it out if you're interested. But for what we're doing, we need to use this factor. It's just easier. If you're going to keep diving into this stuff deeper and deeper and deeper, you're not going to financially make any money in the real world. You've got to crack on. So let's just have a look at this here. So we've got 2 categories here. This is table B3, and in the on-site guide it's I3, I think, but it's the same table. So our cable, we went for 70 degrees C, thermoplastic, singles. We've got not incorporated in a cable and not bunched, which sort of leads you to wanting to use that one. And then this one, incorporated in a cable or bunched. Then we've got some notes here, so notes 1 and 3. 1. See table 54.2 of BS 7671. These factors apply when protective conductor is not incorporated or bunched with cables, or for separate pair protective conductors in contact with cable covering but not bunched with cables. A picture would be nice, I think. Certainly would make it a lot easier. And then note 2 for this one. See table 54.3 of BS 7671. These factors apply when a protective conductor is a core in a cable or is bunched with cables. Now, I know it's not worded very well, but actually we're going to be using this one. And it's the same with the K factor that we're going to use later for the adiabatic. So it is these ones, okay? It's the same as incorporated in a cable or bunched. You get better results. So that factor was 1.2. And we know the length, that was 30 meters. And we know the number of thousand. So we're getting there. We just need to find this milliohm per meter value. Now, we don't know what the C.P.C size is. We know what our live is, that was 4 mil. And with this method, you're just kind of, taking a guess really and just checking it for compliance. So we could start with 1.5, check it for compliance. If it doesn't work, we could go up. So we'll do that. So 4 mil, 1.5, our milliohm per meter is 16.71. So, this is a handy table. It gives you individual conductors, but it also gives you these handy combinations. So what I could do is just take the 4 mil on its own value of 4.61 and add it to the 1.5 value of 12.10. So 12.10 plus 4.61. What do I get? I get 16.71, which is the same, isn't it? So they've done it for you. Again, cheers guys. Just makes my life so much easier. 16.71, which comes out as 0.6 ohms. Add that to our 0.12 and we can calculate our ZS. So our ZS is 0.72 ohms. Our maximum is 1.37, so that complies. And in fact, it's quite a well in, so we might be able to drop it to 1 mil perhaps. But then, I suppose if you're running 4 mils, you've got to think of like mechanical, protection as well and things like that. So I think I'm going to stick to 1.5. And my hunch is that a 1 mil might struggle with the next bit, which is the adiabatic or the thermal constraints. So we know that it's going to generate enough fault current to trip the device, but can that C.P.C, the 1.5, can that sustain that fault current for that time until it disconnects? So that's where this adiabatic comes in. And so we need to know these parameters. Now K does a heck of a lot. It's a factor that takes into consideration basically the initial temperature, the final temperature, and all sorts of other madness. But we're going to go to chapter 54 and page 197 of the regs, and we've got all these tables here. This table 54.2, this is says values of K for insulated protective conductor not incorporated in a cable and not bunched with cables, or for separate bare protective conductor in contact with cable covering but not bunched with cables where the assumed initial temperature is 30 degrees. Lots of words. Think of that as like a supplementary earth on the side of an SWA. This one here is the one we're going to use. Values of K for a protective conductor incorporated in a cable or bunched with cables where the assumed initial temperature is 70 degrees or greater. Because our C.P.C is going to be going alongside other live cables, we're just going to assume that it's as hot as they are. Okay, so use this table then. We need to know the material of the conductor, which we do, copper. We need to know what the insulation limitations are, in this case 70 degrees. And it gives us value here, so 115/103. But there's a little star there, so let's have a look at what that says. It says above 300 millimeters squared. Well, ours isn't, is it? So that means we're using 115. So our K is 115. Now, T, because we know we're under the max ZS, we know that it's going to trip almost instantaneously. Appendix 3 in the regs, time current charts, I'll tell you that. But our T is 0.1. Now this is the fault current that's going to occur due to our ZS. Now it's just, Ohm's law again. But, we can play with these voltages because, you should get to know this stuff and understand what's going on. Now, in level 3, the City and Guilds, but it'll just tell you to use 230 volts. But you could put those C min and C max and just see what happens to the value. Obviously, if we put C max, we're going to get a higher fault current. If I put C min, I'm going to get a lower fault current. I'm just going to stick to 230 just to try and keep this simple. But you know, if you know you're in a high voltage area, you probably want to change that. And if you know if you're in a low voltage area, you probably want to change it as well. And if you're learning, just keep playing with this stuff. You know, put in the maximum possible of about 252 if you want. You know, nothing's going to explode when you're just playing with numbers, and it just helps you understand everything. But for now, I'm just going to stick to UO, line voltage to earth, over ZS, which in our case was 0.72. So our I for this particular circuit is 319.44. So I can put this in now. So it's the square root of 319.44 squared times 0.1 over 115. 319.44 squared times 0.1. Oh wait, no. Square root of 319.44 squared times 0.1115. 0.88 mil. So this is telling us the minimum C.P.C size that can handle this fault current for that time in order to disconnect our breaker. It's come out as 0.88. We chose a 1.5. Happy days. I wonder if the 1 mil would have worked. Let's just give that a quick whirl. So we've just got to basically replace that to get a new R1+R2, new ZS, new full current, and then plug it in. So, 1 sec. So 4 mil, 4.61, that's the 4 mil, and then the 1 mil is 12.0, no, 18.1. So that's my milliohm per meter times 30 times 1.2 over 1,000. So that would change to 0.82. Add that to my ZE of 0.12. So my new ZS would be 0.94 ohms. So still complies. And then just check the adiabatic with that. So I need a new fault current. I could be fancy pants and put it in like that, couldn't I? So I've just replaced the I with the equation to get I. Don't have to do that, obviously. Squared times 0.1 over 115. 0.67, so we could have used 1 mil, but as I say, sometimes you want a bit of mechanical strength, and that might be a consideration as well. So in total then, that circuit is going to have 4 mil line conductors, 4 mil neutral conductor, if it needs it. It's 3-phase induction motor obviously, so probably don't need it. 1.5 C.P.C. The only reason you may need a neutral, some controls for the motor might need it. Obviously, yeah, as it's a motor, it probably need other types of protection as well, like under voltage protection, stuff like that. But there we go, that's the cable selection done. Happy days. Okay, so C.P.C method 2, very similar to method 2 using the volt drop. We're going to rearrange this R1+R2 equation for maximum milliohm per meter. And we know that our live cables are 4 mil. So this is about choosing the C.P.C. So we need to kind of play with this and find out how to transpose this really to get maximum milliohm per meter. So first, we can get that ZE out the way. So that would end up like that. That's dealt with. We can also do that already. Now this is like the maximum ZS. So what we're trying to find is the minimum C.P.C that will work. So we put in our max ZS of 1.37 ohms for that protected device. Take away our 0.12, and that gives us a target for our R1+R2. So we've got 1.25. And that's the maximum resistance or impedance our live and earth can be. So we need to kind of expand that a little bit. The equation for that times that temperature factor divided by 1000. So what we do, we transpose for that, and then in the same way we did with the volt drop, we can, use this table here to find a maximum milliohm per meter value. So transposing that, you'd multiply out the 1000. I need to actually write an equation here, don't I? I'll tell you what, I'll do it down here. So R1 plus R2 equals a milliohm per meter times length times temperature factor over 1000. And like I say, we'd multiply that out, copy it that side, cancel, and then you've got R1 plus R2 times 1000 equals milliohm per meter times length times temperature factor, and then we just divide out these, copy it that side, and cancel, and then we've got our equation. So our milliohm per meter max is equal to the maximum R1+R2 times 1000 divided by length times temperature factor. We got that. So it's 1.25 times 1000 divided by length times the temperature factor. So our maximum milliohm per meter value then, 1.25 times 1000 times 1.2. So our maximum milliohm per meter value, 34.72 ohms. Now, milliohms, sorry. Now we've got our live cable already, that was 4 mil. So as long as our milliohm per meter is under this, we're alright. So 4 mil, 1.5, that would work. 4 mil 2.5 would work, 4 mil 4 mil would work, so any of them would work really. We could check the 1 mil, so 4 mil on its own is 4.61, 1 mil on its own is 18.1, and add them to that comes to 22, so that would work as well. I think 1 mil is probably a bit too small mechanically, it might get bashed about a bit, so we could select 1.5. That makes sense. So 16.71, that gives us a value of, and we'll need that in a minute because we need to calculate our actual ZS before we use the adiabatic with this method. But that's how we could choose a C.P.C using it in a different kind of way. So at the moment we're saying 1 mil would work, 1.5 would work, 2.5, all of them would work really. I think I'm going to go for 1.5, but as I said, value engineering and all that jazz, probably get shot if you went for 1.5, so be careful. Next then, we need to actually work out what our R1+R2 actual is. It's the same equation. So I said, remember that number, 4 mil 1.5, 16.71. So 16.71 milliohms per meter times by the length times by 1.2 over 1,000. So 16.71 0.6. We did that in the last method, which means our ZS then will be our ZE plus 0.6, which equals 0.72 ohms. So now we use the adiabatic like we did before. So S equals our fault current then, I, we need that, 230 over 0.72. .44 amps. Our K values still 115 and T still 0.1. So 319.44 squared times 0.1 over 115. You know what it's going to be. .88 millimeters squared. So the one we chose is more than that, so tickety-boo. So all in all, our live is going to equal 4 mil. C.P.C will equal, well, whatever you like really, 1 mil, 1.5, they all work. I'm going with 1.5. Any neutrals, obviously, if you need them. I mean, this induction motor probably doesn't need them, but as I say, some controls and things like that might need them. There we go. So that's method 1 and method 2 sorted. I hope this helps. I hope it's not just a waffling mess. But I'm going to be doing more of them, so let me know if it is. Okay, see you guys, bye.